Hi, and welcome to our webinar, Advanced CO2 Consequence Modeling for Safe CCS.
KFX is DNV CFD code, which can be used for dispersion, fire, and explosion simulations for hydrocarbon, hydrogen, ammonia, and of course, CO2. This picture is to illustrate the complexity of CO2 dispersion. As mentioned, CO2 is often stored at liquid or supercritical conditions. And in the event of a CO2 release, there will typically be a cold CO2 jet, which can be a multi-phase jet near the release point. That means that a part of it may become dry ice, so we'll have a solid vapor two-phase flow. Air entrainment happens throughout the entire dispersion. And as previously mentioned, CO2 is heavier than air. Therefore, a dense CO2 gas cloud follows the ground. The obstacles such as trees, buildings can affect the dispersion behavior as well as terrain. And we also have to take into account different atmospheric conditions. Consequently, reliable CO2 dispersion analyses are needed. I would like to show you a case study which we carried out in recent years. This is 570 tons of CO2 stored at 16 bar in a liquid phase in a tank that you can see here. Due to mechanical failure of the pipe, CO2 is released into the atmosphere as dry ice particles and CO2 gas with a constant mass flow rate, and we then follow the evolution of the cloud with time. It is also possible to model time-varying releases. This can be done directly in KFX, and it's also possible to use Phast input. In this scenario, the wind is blowing from the sea towards the hill, so a different direction from the release, which is downwards. So what will happen here? So we used KFX to model this scenario. And what we can see is the 4% concentration ISO surface of the CO2 cloud. The dry ice particles sublime during the dispersion process, cooling down the cloud and making it even heavier. This has also been observed in experiments we have compared it with. This is a downward release, so there's also less mixing with the surrounding air, which leads to a higher concentration of CO2. We can see that the cloud interacts with the topography and obstacles, such as building, but I think it will show better on the next slide that I will present. So this is a snapshot of the same simulation. This is at 15 minutes from the start of the release and from above. It shows the projected maximum of CO2 concentration ISO contours. The red zone, which as you can see is quite large, represent a concentration of CO2 higher than 15 volume%. We have observed that when taking into account multi-phase release, higher concentration of CO2 is maintained for a longer time. What we can see on the picture is that the facility behind the tank on the right-hand side here act as a barrier, so we can see the effects of geometry and terrain. You can see here that is a small hill, and you can see the cloud goes around it. So reliable CO2 consequence modeling, accounting for the effects of CO2 thermodynamics, atmospheric conditions, geometry, and topography, is a key to safe full-scale CCS. And that is one, at least, of the reason why we are currently running a KFX CO2 joint industry project together with Equinor and Total Energies. We aim to improve the models in KFX so that it can model accurately dry ice formation, deposited CO2 solid particles on the ground, sublimation of CO2 particles in the gas cloud, and the resulting dispersion, all taking into account topography, geometry, and of course, atmospheric conditions. This GIP started in 2019 and will conclude this year. The results from this GIP will be made available in the commercial version of KFX as soon as possible in 2025. The picture you can see on the right here shows the CO2 gas concentration contours for a high pressure release and the dry ice particles. The CO2 particles are not reaching the ground because they are subliming. And this is actually from a scenario from one of the BP and Shell tests that Jan mentioned earlier that were carried out in the 2000s. So talking about these tests, they have also been used to carry out validation for the CO2 model in KFX. You can see here two graphs, on the left for the BP tests and on the right for the shell tests, comparing the maximum CO2 gas concentrations obtained at measurement points downstream from the test and the scenarios modeled with KFX. The experiments are represented by a cross and KFX scenarios by a circle. So as you can see, the curves for the experiments and KFX follow the same pattern and even merge for some of the data. So we can say that there's a good agreement between the experimental data and the results from KFX. Validation is always part of our software development process, and as such is also a consequent part of the GIP. Experimental data available, such as the kosher test, is also being used to validate KFX for CO2, and the results look promising so far. On top of validation, there are several activities being carried out as part of the KFX CO2 GIP, and this summarizes what has been done so far and what remains to be completed. So the activities focus on one side on improving the source term modeling so that KFX can model multi-phase release, taking into account dry ice particles in the gas flow, but also deposited solid particles on the ground. The other part is to improve the models for gas dispersion, specifically the treatment of wind boundary condition and atmospheric turbulence for far field dispersion, including the effect of water vapor condensation. And of course, as mentioned, we need to be able to account for geometry, so buildings and so on, terrain like hills and valleys, but also vegetation. And I would like to spend just a bit more time on that last part, showing you the effect of vegetation on gas dispersion. So a forest creates a large wind drag, whilst only a few % of the volume is occupied by solid. This enables holding back and slowing down the spreading of gas. For dense gas, such as CO2, this also means that higher concentration of CO2 remaining closer to the leak point can be much larger. And this is actually what is illustrated by the picture you can see on the right. In former studies in KFX, we have used thin porous wall to model drag from vegetation. This works for a small region of vegetation, but to model a forest or a large area of bushes and trees, the surface porosity approach is very grid dependent. So we are currently developing KFX so that forests can be modeled as a combination of cones and cylinders and regulate how much solid fraction they generate. So as I said, the result from this GIP will be included in the commercial release, but not before the end of the GIP, so 2025. We are also discussing opening a second phase to focus on other topics, such as CO2 subsea release modeling, which brings my presentation to that topic exactly. CO2 releases underwater. Offshore CO2 pipelines might be a major hazard for the safety of ships, offshore infrastructure, and for the marine environment. A pipeline failure will lead to the formation of CO2 plume underwater, and the dissolved CO2 will impact the acidity of water, which affects marine life. The plume may also reach the water surface, resulting in toxic levels of concentration in the atmosphere. Therefore, there's a need to perform large-scale CO2 release experiments to first establish a scientific understanding of the behavior of CO2 leaking from underwater high-pressure pipelines, and second, understand the impact of such releases on the safety of shipping and offshore infrastructure in order to further develop and validate CFD models. This will provide crucial input for quantitative risk assessment and thus contributing into setting up safety guidelines for CO2 offshore pipelines. So talking about understanding underwater CO2 releases, here are the questions that we need to answer. How is the plume of the release affected by a current above the release? How much of the gas is dissolved in the water at real large-scale conditions? At what releases rates, depth would the bubbles start reaching the surface? What concentration of CO2 is recorded at the surface above the release? How is the dynamics of the bubble zone and how can the interface be modeled in the best way possible? What are the safety distances on the surface for personnel for different subsea release rates? What is the extent of influence zones for marine life for different subsea releases? And what are the capabilities to predict both the subsea and atmospheric CO2 plumes? The sub-CO2 joint industry project is currently ongoing phase 3 to provide valuable insight in this regard. Phases 1 and 2 were previously carried out at Spadadam Testing Center, and I will show you some recording just in a few moments. First, I just wanted to show the experimental setup for this phase of the GIP, which looks at releases around 40 meters deep. Phases 1 and 2 looked at releases from between 3 and 4 meters and 10 meters deep, respectively, with a similar setup. So this is a video recorded from one of the experiments carried out during the previous phases of the sub-CO2 GIP. The depth of the release location is 3.8 meter. The hole size is 4 millimeters and the direction is upwards. The apparatus you can see on top of the tank is where sensors are located to measure the temperature and the CO2 concentration in the air. In this scenario, the gas reaches the water surface in kind of big pockets, which makes the water rise, and we can see how turbulent the water surface gets here. This is kind of like a blowout scenario, but with CO2. This is another experiment, this time recorded underwater. In this scenario, the release direction is downwards for a 4 millimeter hole. In this scenario, because the release is downwards, it impinges on the floor, which will result in a wider plume. The upward release has more of an arrow shape and is narrower. So as mentioned, one of the benefits of large-scale tests is to increase knowledge of on CO2 behavior in such releases, so as to further develop and validate the CFD model. This animation here is an animation of a natural gas subsea release modeled by SINTEF's SURE model combined with KFX for the gas cloud dispersion above the surface. Here, SINTEF and the KFX team in DNV have collaborated to develop an interface between the two models so that SURE data can be used as input to KFX in order to model a release all the way from underwater to atmospheric dispersion. So with the KFX CO2 GIP development, the aim is to make such scenarios modeled for CO2 as well. Finally, I'd like to briefly summarize DNV's expertise in CCS so far and take a look at some of our development activities. DNV has been investing for safe CCS through numerous research and joint industry projects together with partners, some of which mentioned here on this slide. These projects have led to the development of DNV recommended practices, as well as DNV frameworks for assurance services and complying with international standards. In the past 10 years, we have helped our customers on more than 200 projects throughout the CCS value chain by providing different services in carbon capture, transport, and storage. This has helped us gain more knowledge and insights and become an expert in the industry. When it comes to consequence modeling in particular, DNV Risk Advisory has gained extensive experience in conducting consequence modeling and risk assessment using DNV digital solution tools on key CCS projects in the UK, such as Track 1 and Track 2 clusters, but also globally. These are some of the projects that DNV is currently involved in together with partners. The sub-CO2 GIP that I've mentioned previously, that is currently undergoing phase 3, looking at CO2 subsea release 40 meters deep. The CO2 safe pipe joint industry project, which aim is to close knowledge gap identified in the transportation of CO2 in pipelines, covering CO2 in both gas phase and dense phase, CO2 stream composition and its effect on corrosion and material, and the risk of running ductile fracture. The GIP's outcome will enable both the safe and cost-effective design of new CO2 pipelines and the repurposing of existing pipelines. Skylark. So the primary objective of Skylark is to address upcoming challenges related to the safe operation of CO2 pipeline. This includes enhancing the understanding of source characteristics, terrain effect on dense clouds, emergency response protocol, and operational issues as venting. The focus on the KFX CO2 joint industry project is to enhance the software's capabilities, including detailed simulation of complex thermodynamics and heat transfer processes, and dry ice formation caused by a release of liquid CO2, in order to provide a solid basis for improved CCS safety and for finding cost-effective technical solutions for design. You can find more information on these different projects and more on our website. Finally, to summarize, research and development play a pivotal role in advancing our understanding of the atmospheric and underwater CO2 releases and dispersion and its associated risks. GIP between DNV and partners contribute to developing models for our tools, Phast and KFX, to handle key physical phenomena related to CO2, such as sublimation, solid deposition, craters, time-varying releases, topography, vegetation, and so on. Such projects also provide crucial input to setting up guidelines for safe CCS. Through its activities, DNV continues to be on the frontier of understanding CO2 behavior, being a trusted partner for the whole CCS value chain, and aligning with our purpose to safeguard life, property, and the environment.
Thank you to our audience for joining us today. We hope you found the information useful in your work. See you next time, and goodbye for now.